Hi everyone, my name is Gau Qi Sheng from Department of Mathematical Sciences, Faculty of Science, University Technology, Malaysia. Today I'll be presenting about my research on solving the stochastic vehicle routing problem using a deep reinforcement machine learning method. The vehicle routing problem, or VRP, is a foundational issue in the transportation and logistics sector that aims to find the most efficient routes to minimize the cost for vehicles to deliver products to multiple customers. So, traditional methods often face significant scalability and adaptability challenges. To overcome this, deep reinforcement learning, or DRL, offers a solution by learning optimal policies through interaction. Therefore, this paper proposes a deep reinforcement learning DRL approach to create a scalable and adaptive solution for the dynamic large-scale vehicle routing problems. So this project has three objectives. First, to develop a mixed integer linear programming, or MILP model. Second, to evaluate the performance of the deep reinforcement learning algorithm using three different inference strategies: the beam search, the greedy search, and random sampling. Lastly, to incorporate stochastic weather in deep reinforcement learning algorithm. Past researchers has revealed that the limitation of traditional VRP methods. For example, the exact algorithms are computationally infeasible for large-scale problems, while heuristic methods, for example, n-colony optimization (ACO) and genetic algorithms (GA) require extensive tuning and lack adaptability for this kind of problem. In contrast, deep reinforcement learning emerges as a superior approach that learns a general adaptive policy through interaction with the environment. To achieve all the objectives mentioned above, this research follows a clear methodology. First, the problem is defined as a stochastic vehicle routing problem where customer demands are uncertain and influenced by simulated weather. Second, the solution is built using an actor-critic deep reinforcement learning approach. The agent will learn a routing policy through an advanced encoded attention framework. This approach also introduces a masking technique to ensure all routing rules, like vehicle capacity, are respected. Third, for data generation, the model is trained on dynamically generated synthetic data. This means that the customer locations are fixed, but the weather and demands are different in every training instances. This will force the model to learn a robust and general policy. Finally, to test the trained agent, three different inference strategies are used: the greedy search, beam search, and random sampling. These inference strategies will translate the learned probabilities into final routes. Now, for the preliminary result, currently a deep reinforcement learning agent is trained for basic vehicle routing problem without the stochastic weather and demand. So as you can see from the graphs, the training was successful. The average rewards consistently increased, while the losses stabilized. This shows that the agent was effectively learning. This example Python loggers shows that one of the routing for the random sampling inference. The most significant finding came from comparing the inferences strategies. The route plots here show the solution generated by three different inference strategies. This research discovered that random sampling achieved the best performance, outperforming both greedy and the beam search strategies. This is a powerful result as it indicates that the agent has learned a rich exploratory policy and not just a simple obvious one. So this research advances the field of AI-driven operation research by developing an adaptable deep reinforcement learning framework. It is a powerful method for tackling the computationally complex vehicle routing problem, bridging the gap between the theoretical deep reinforcement learning and practical application, which could be applied to industries such as e-commerce, manufacturing, and healthcare. Its ability to adapt to real-world uncertainties such as fluctuating demand and weather leads to reduced costs, reliable delivery schedules, and improved overall efficiency. In conclusion, this work successfully trained a deep reinforcement learning agent for the vehicle routing problem. So the preliminary results from comparing inferences strategies shows that random samplings achieve the best performance, indicating that the agent has learned a rich exploratory policy. So this provides a strong foundation for tackling the full stochastic vehicle routing problem and demonstrates the real-world value of applying advanced artificial intelligence to logistics. That's all from me. Thank you.